All right, so let's get started. Module 3, it is on structures, mechanical structures. What is a structure? Basically, when we combine two or more than two or three components together, we build something which we call it a structure, or to be specific, mechanical structures. This module is a fundamental topics in statics. I would say any design, anything that in future you start designing after the first step, which is the concept design, when you sketch something and you get to what you want, then this step, like which you study in module 3, is basically the foundation for the design. And no matter what you're designing, the design can be a chair, it can be a simple device, it can be a complicated mechanism. It starts with force analysis, and you need to know how, when you apply external loads, what is the reactions on each members, so you can analyze the stresses, and then you can pick the right material or select the right size to basically avoid failure. All right. So, but this chapter, this module focus only on force analysis. Let's get started. Well, to start with, we categorize the structures to three main categories: frames, machine, and trusses. In some textbook, all of these three categories consider one. They call it a structure. So there is no basically distinguish between them. But this is some sort of a common maybe sense, and that to categorize them like in this way. But later when you solve problem, you see really there is no specific distinction between them. So a frame, we say it's more like a fixed structure. There is no moving part in it. Like this one, like this chair, we can consider it as a frame. Several parts like this, you see this link and the other links, they are all pinned together or maybe bolt together, and there is this bag on top of that. So we call it a frame. No parts here is moving. Everything, they are all fixed together. The second category is machine. The difference between frame and a machine is that in machine, there is moving parts, like these pliers, right? You can open and close up these pliers, right? And depends on the force that you apply, you get different reaction to this part D over here. So then the only distinction between machine and frame, machine has moving part, frame doesn't, all right? And then the last thing is trusses or truss. Truss is more like frame, no moving part, but the only difference is we say truss is more like a larger structures, but more important is in truss, all the members, they are linked, like each of them connected at only 2 points, like this member GF, you see, it's just one link, or BG, it's just one link. And all of them, they are connected at the two ends. Like you cannot find any members that connected in the middle, right? You see? But here in this frame example, in this chair example, for example, this link ACD, or maybe this bigger one, this link HFB, they are connected at 2 or 3 points, right? They're connected here, they are connected there, right? And also we consider the connection or contact to the ground also one connection. That's the only difference between truss and frame, which we will discuss more in trusses later. As you can see, fundamentally they are the same. What is our objective here in this module is to find the reaction forces when we apply external loads. For example, in case of the chair, we are interested to know if somebody apply, let's say, put this back there, or somebody sit on this chair and you have an external load W, then what is the reaction at each point? Maybe later we want to design these C, the pins at C, F, and so on, or each part of this chair. In machine, the same. We want to know when we apply this load P, how much is going to be the force that we apply to this basically part D, all right? And sometimes we may also interested in designing the pin here, pin A. So we need to know what is the reaction at this pin, right? If this is a pin A, we want to know how much force when we apply these external loads exerts on this pin A, so we can design a pin not to fail. The same with trusses. We want to know when, let's say, this truck is passing through this bridge. It has a weight. We want to know what is the force in each individual members to make sure that this truss is not going to fail. So in other words, we want to find out the reaction forces when we apply external loads to each structure here. What is the solution? What is the method that we are going to take? Static, there is no formula or anything except those three simple formula that we learned before, that always sum of the forces in X must be 0, sum of the forces in Y must be 0, and taking the moment about any point, so here it can be any point, right, must be 0. This is our only tool, and we always start with free body diagrams. So as I said before, the most important element in solving the problems in static is the FBD or free body diagrams. If we can draw a nice, clean, and correct free body diagram, the rest is just plugging some numbers in these three formulas. So let's quickly review the free body diagrams. So free body diagrams, essentially, we said you free the part from its connection, right? And for each support or connection, you put a reaction load, right? So we start with a very simple case of a cable. In a case of cable, you saw the reaction is just one tension in the cable, right? Which we can call it T or F or whatever, it doesn't matter. Like here, I separate this basically box or whatever it is from its connection, which is this cable. I imagine that I cut this cable, so it's going to be one reaction T. So another connection which is very, very similar to cable is a link, basically. So a link behaves more like a cable. It applies one force, a tension. The only difference between a link and between basically a cable is a cable only apply tension. So this is cable, remember, only tension. For example, you cannot say that I have a cable here and this cable is, let's say, applying tension here, right? If you have a cable, you cannot really compress it. It's just going to jam, right? So this is then wrong. But if you have a link here, a link can also have a compression load, right? A reaction like this one. Let me draw it a little bit over that side. So we say a link can apply both tension and compression. I remember when I had this course, our Mech 260 was really, really strict. And somebody, when he draw a free body diagram for a cable, for the cable, he put a tension load, a compression load. And the teacher like crossed all of his solution, and the teacher said, you didn't understand the concept because a cable really cannot apply compression. Although his solution was correct, but he crossed it. Don't worry, I'm not that strict. But remember, a cable always apply tension. A link can have a tension, more like a cable, and also it can apply compression. So the next support that we learned was a simple support, or something that we call it a roller. We said roller, We show it in different forms, maybe just by a roller like this one. And a roller always apply load, basically, which is perpendicular to the ground, right? And it doesn't matter in any form that we show it. When we draw the free body diagrams, this is the reaction from a roller, right? And the roller, again, can be on the ground. It can be on a wall. It doesn't matter. We just need to be careful that the force is perpendicular always to the ground that we apply the load. So the next one was the joint or a pin. So a joint or a pin, we said it has two reactions. Like here, for example, we can call these two directions X and Y. So we can call this one AX and this one AY, basically, right? And we said, well, if, let's say, if you have a box, maybe a door or maybe something joined here to this ceiling or whatever it is, we say this box, we cannot move it really to the left or right. We cannot move it ups and down. So it means this pin can apply two reaction, right? And here you see there is the actual 3D image of that joint, or a joint, not that joint. And as you can see, this link can easily rotate around this axis, right? It can rotate around this axis with no constraint. But if somebody tries to move these, basically a link, let's say in X or in Y direction, then there's going to be reaction from this link. In other words, if, let's say, if I call this one X, Y, this one has to be Z direction, right, to follow the right-hand rules, then we say we cannot really move this link in X direction, so it's going to be a reaction in X, it's going to be a reaction in Y, and also it's going to be a reaction in Z direction. In fact, we cannot move this link in Z direction, or in this 2D frame, I cannot take this box out of the screen or push it into the screen, right? But since we are dealing with 2D problems, and again, we are not applying really any load here in this scenario to the screen. By to the screen, I mean applying a load in Z direction. We are not considering this AZ. So this is then AX, this is AY, and this is AZ, which we are not worried about this AZ, and we consider it to be 0. And eventually, a fixed support, as the name implies, it is fixed to the wall. And similarly, if I draw like here, the X, Y, and Z direction for this link, let's say this is my Z direction, then we cannot move this box or this whatever beam or whatever it is in X, Y, or Z direction. So simply I say it's going to be reaction if I want to move it ups and down, or if I want to move it left and right, or if I want to push it out or inside this wall, right? It's going to be reaction there. In other words, if I draw the 2D version of it, which we care more, this is the 2D version, and we say this is, let's say, the wall. And always in a schematic, we use this sort of sign or this symbol or schematic to implies that it is a fixed, basically, support. And if you're dealing with a fixed support apply load in axial load. You cannot move it left or right. You cannot move it ups and down. So these two supports. The third one, which is like I show it over here, if I want to name them, then it's going to be, let's call this one maybe X, call this one Y, and then this one is Z direction, right? then this one is my AX, this one is AY, right? And AZ, we don't care about it, it's going inside the screen. But there is a difference between this support and previous one. Previous one, easily we could rotate it, right? We could rotate it with no problem, rotation. But this one, I cannot rotate it. If I try to, let's say, bend it down, it's going to be a reaction. And that reaction is a moment. So, which we call it, let's say here, M0 or MA or whatever we want to call it. It's going to be a reaction. So remember, a fixed support always has three reactions, AX, AY, and a couple or a moment, all right? Which doesn't let us to bend something. So this is basically the main supports or connection that we are dealing with in this course. As you can see, you don't need to memorize anything. They're all common sense. And you start with simple scenario when you draw the free body diagrams, and you make it, you add to it to draw the full free body diagrams. So what's the next things in free body diagrams that we should know is something we call it two force members. Sounds a weird name, two force member, but let's see what it is really. And I want you to pay attention. It's really silly and it's really simple, but for some reason, I don't know why students make mistake when they solve problems and they forget this silly, simple concept, okay? So let's say you have a link here, this link AB, and this link AB, we are told that this link has been pinned or joined at A and B, all right? So pin or joint, remember the joint connection, it can rotate easily, right? We don't care about the rest. Maybe at A, we have a box or other things, other members that has been connected to it, and B, maybe it's a big part connected to somewhere else. We don't care. We just focus on this link A and B. So if I draw the free body diagrams for this link, so the free body diagrams, let me draw the link again so my picture doesn't get, the image doesn't get messy. So let's accept that this is the link. And this link over here, and then okay, so this is B and this is A. So we learned that a pin or a joint connection has two reactions, AX and AY, right? So, and we are allowed to choose the direction as we want. Let's say I choose for simplicity my X direction to be like long links. And let's call this one the Y direction, right? There is no limitation in the way that we pick X and Y. So this is X and this is Y. So, and as I explained, we need to have two reactions. At B, I'm gonna have two reactions, BX and BY. At A, it's a pin, I'm gonna have AX and the same AY, right? And as I said before, we don't worry about the direction of these. We just assume they are positive, and by positive, I mean they are in X direction and Y direction. So this is then gonna be BX, and this one is BY, and this guy is AY and AX. All right, so this is simply the free body diagrams, the FBD of this system. Okay, so I have the free body diagrams. I know I am in a static, and I know in a static, some of the forces in X must be 0. So in X, what do I have? I have BX plus AX equal to 0. One equation. Now I know some of the forces in Y must be 0. Then AY plus BY must be 0. And I know that taking a moment about any point, let's say we take the moment about point B must be 0, or A, doesn't matter. If I take the moment about point B, what do I have? Well, these Bx and By, they are passing through this point. Their moment is 0. And what about this Ax? Ax is passing through this point. It's also 0. I ended up only with Ay. Multiply, let's say the length of this link is L equal to 0. From here, I get Ay equal to 0. So if I substitute, let's say this is equation 1, 2, and 3. So from here, then, if I substitute in 2, I can realize that By also has to be 0. What else? Well, we found Ay 0. We found By 0. And from 1, we can conclude that Ax is equal to minus Bx, right? So this is what we got. What I can conclude now that if I have a link like this AB connected at 2 points A and B, the reaction is something along this basically line. Let me draw this line. The line that connects this A and B. And we call them, maybe we said Ax is equal to minus Bx. So it's going to be then, let's say if this is Bx, then Ax is going to be opposite direction, right? We just found Ax is minus Bx. So the opposite of what I just drew here, all right? And these two, they are equal, basically. This is what we found. We found that if this force is, let's say, F, this one also has to be F, whatever it is, right? This is what we found. So this is something we call it a two-force member, right? Probably you say, okay, well, that was obvious. If you have a link, the link apply a load, which the load, it's applied at two ends, and it is, the loads are collinear. They pass on the line that connect these A and B. Well, that's correct. But this is something that when you draw free body diagrams, you should know that, all right? But something more important that you should know is, for a link, it's obvious, I agree. What if instead of a link, I have, let's say, a shape like this one, like a half circle? The link is something like a half circle. Like this is B and this is A, all right? So what can we say now? Let's say you replace this link AB with a half circle. So can you guys think for 10 seconds and see if we write down the same formula, the same concept that I just draw here for this one, can I make the conclusion that the force or the reaction is along this line that connect these 2 points? Is it plausible, or no, it doesn't make sense?
Yeah, it should work the same as the previous one, I think.
Yeah. Thanks, Oliver. As Oliver pointed out, exactly. It doesn't matter what is the shape. If it is a link, it's a half circle. Let me go there. Okay, this is the link, right? You guys can see the link. So for a link, if I apply load, let's say tension, right? If I apply load, let's say a tension load or compression, the tension is going to be along the line that connect these two together. So if instead of this link, now if I have a half a circle, that's going to be the same concept. Let's say if I have these two cables, pretend that they are cables. If I apply a tension, right, this tension definitely has to be along the line that I'm connecting these two together, right? Something like that. Right? So a cable, I apply a tension, right? And this tension has to be in this line. So you may say, no, I can apply a load like that one, like this line. Then I apply the other load like that one. Let's try that one, right? Somebody try to apply load in these two directions. If I apply the loads, what will happen? You see these things rotate and balance along these lines. So always the reaction is along this line, right? In this scenario, of course, because I have a cable, I cannot apply a compression because everything's jammed. I can apply tension, but no matter if I apply a compression load here, the same concept. The compression is going to be along this line. And it doesn't matter if it's a link, it's a half circle, or maybe a L shape, right? Same concept. If it's a L shape, like this one, you apply load, either tension, or you apply load compression, the reaction is going to be along this line, right? And this thing doesn't have to be a 90 degree, or it doesn't have to be the same size on two sides. It can be, let's say, something like that. The same concept, the reaction is going to be along this line that connect these things together, all right? So that's your reaction when you draw the free body diagrams. And the shape can be any complicated things, like even an S shape. The same concept, the load is along the line that connect basically these two lines together, right? Hope it's clear. I know it's very simple, but again, as I said, for some reason, a student make mistakes, they forget about it, and always I'm surprised why this silly concept it's become complicated for the students, in fact, but not for you guys, right? Now you got it, okay? And it has a silly name, two force members, because it only has two force at its two ends, all right? So keep in mind, a two force member has to have three conditions, all right, to satisfy these two force member things, all right? What are those three? First, connect only at two ends, at 2 points, at 2 points, right? So connects only at 2 points. All right, that's one thing. I have to work on my handwriting. Emily knows my handwriting. How's my handwriting, Emily, on Blackboard?
It's good.
It's good. All right. All right. So I'm practicing. All right. Let's get here. So Emily was my student last semester, dynamics, Mano 265. Maybe this course now is boring for her because it's static. Everything is fixed, not moving. But dynamics, the same things, but everything's in motion. If you guys are interested in mechanics, in designing mechanism, I suggest that course, but that's a tough course. You can maybe talk to Emily. All right. Connect only at 2 points, A and B. That's one condition. So no weight, or in other words, we neglect weight. So like this link AB, if the weight is too much, it's something we cannot neglect. Let's say if it has a large weight of W, then it's not a two force member, because now it's a three force member, right? We said it has to only has connected at 2 points and no weight. And then the third condition, no external load on it, right? If it has a weight, it means the third condition, we are not satisfying the third condition, and which is not good. It's not a two force member. So we should be allowed to say that weight is so small compared with other forces that we can neglect it. So it's negligible. All right? So that's two force member. Let's solve some problems, some examples, so you can understand these topics very well. We'll start with this one. We want to draw a free body diagrams. Everybody has 30 seconds to draw the free body diagrams for this one. First, try to understand how this mechanism or this frame works. We call it a frame, right? Remember the categories: frame, machine, and trusses? It goes more to the category of frame. Then try to see if there is any two force members. And if there is, then draw the free body diagrams for me. You have 30 seconds while I'm drawing this link here for you guys. Yeah, try to do it on your paper. And then we do it together. We'll see what is the free body diagram. So you're asked to draw the free body diagrams for this guy. So, and remember we said free body diagrams, you need to separate it from all connection, because everything has to be free. And if like there is a frame like this one which has two members, remember that you need to disassemble them as well, right? No matter how many members has a mechanism, you imagine that you are a mechanic and you open all the links and connection and disassemble them. All right. So not to get confused, this is, we put the points by name there, F, this B, this is C, this is A, and this is B. All right. So we want to draw the free body diagrams for these two members. Let's do it. So external loads, that's the easy part. We know that. External loads, we have a force F here. Okay, maybe this point was an F, in fact. A, B, C, D. This point was D. Right? The name of this joint is D. So the force, the external force, is F, right? Well, we start with C. C is a joint. And for a joint, we know that it's going to be what? It's going to be CX and CY, right? That's easy. CX and CY. So what about these L-shaped things? I hope you guys realize that it's a two force member because there is no external load on it. The question didn't say anything about the weight. So and it's connected at 2 points. So it is safe to say that it's a two force member. And if it is a two force member, then I can easily say this two force member, it has a load at two ends, which is, with these two loads, they are collinear, right? They are along this line. And the same for the reaction for the other one. So that's the same line, right? And if that's the same line, then this is going to be the reactions. So it's going to be reaction here, and it's going to be reaction there. So this reaction, let's call it maybe F, or whatever we want to call it. So, oh, if that one is F, let's call this one P. This one has to be P. This is action, this is reaction P. So this is the free body diagrams that we wanted for this problem. Later, we can use this free body diagram to solve the problem if we have all the information like the geometry. For example, for this problem, we need to have the size, we need to have this angle, alpha, and so on. All right? Any question for this one? Seems simple, right? If that's the case, then let's go to example 2. Again, I want everybody to think for 30 seconds, try to draw the free body diagrams. It's very similar to the previous one, but this one also, we want to do some calculation. So again, remember, you need to disconnect, disassemble everything. So everything has to be free to move. So I can think that I have A, B, C, they are joint. I take my wrench, open all these bolts or joints. So I ended up, let's say, with this part. While I'm drawing this, I want you guys to think. So that's that part. Sorry, okay. So hope you guys figure out, first of all, the two force member. Probably all of you are nodding now that AC is the two force members. You know, guys, one challenge for online teaching that I realize is in a classroom, by looking at the students from the face impression, or by nodding, I can realize if a student follow the topics or they got bored. But here, well, I don't have that luxury. So if you cannot follow something, please do not hesitate. Just unmute yourself and jump in and ask your question. Okay, let's do it. Let's draw the free body diagram. So AC is a two force member. We know two force member, and basically the load or the reaction has to be along this line, whatever the reaction is. All right. So we'll start with external loads. So then this is the line. Let me draw it. I draw the same line here, so I know which one is which. Okay. So let's see what we have. We have two external loads. One is this guy here, 600. This is 400. That's good. And then the rest, they are all reaction loads. Let's put them there. So we start with B. B has two reactions, Bx, By, Bx and By. As you see again, I don't care about the direction, right? By direction, I mean I don't care if it is positive or it is negative. I let the math to find out. And always I put the basically the reaction in a positive direction for X and positive direction for Y. So always to the right and up, we consider it's positive. So what else? Well, this two force member, we know something important about it, and we know this two force member, it has two loads at its two ends, and these two loads, they are collinear. You may say, well, in previous example, let's jump back to previous example. You draw it that it is under tension, right? This load, P, is under tension, as if you are stretching this L-shaped link. But you may say, why here you draw a compression? Again, that's something which doesn't matter. You can assume compression like here, or you can assume tension like this example, and you just let the math find out. If you end up with the negative numbers, it means the direction that you picked or your first assumption was wrong. But sometimes it's common sense. Like here you can see in this mechanism, if you apply load F, most likely this AB is under tension. If you draw a tension load, then the reaction here is going to be a tension load, right? The opposite and same force. Here, if I apply this load, it's sort of I can it is intuitive to think that this is under compression, but again, doesn't matter. You can draw it as a tension load. So what is the tension? We don't know. Let's call it F. All right. We don't know the value. We call it F. And if I show F in this direction, the reaction, remember, it's the same load, but opposite direction on the same line, F. All right, so this is what I got. The load, let's say this one is 600, and this one is 400. Good. Now, if I look at this diagram, how many unknown I have? 1, 2, 3. Remember, in static, we have 3 equations. We can only solve problems that have 3 unknowns or less. Remember from the last session, we call if you have more than 3 unknowns, it is called indeterminate. You cannot find it. You have to rely on other tools. So this one is a determinate problem because it has 3 unknowns. And remember why 3 unknowns? Because we have 3 equations. Sum of the force in X, sum of the force in Y, and total moment, they must be 0. All right. There is no specific rule which of them we should start. You can start from sigma fx or you can start from m. So there is no specific order. But I suggest always start with taking moment because you can get rid of some unknown. And then take the moment about a point where you can get rid of most unknown. Here is bx and by, right? So if I take the moment about b, you see, easily I get rid of bx and by. So let's write down for the rest. I have 600. The distance between the line of action and B is 100 millimeters. We keep the units as millimeters. And it's try to rotate it counterclockwise, so it is positive. The second one is 400. Is 400, the line of action between this guy, let's see, between this guy and point B, we see the distance is 160, and it tried to rotate it counterclockwise. Hope this concept of moment now becomes easy for you. It's just very simple, right? Force multiplied by the distance, and the distance is the perpendicular distance between the point and the line of action. And try to visualize how these forces try to rotate these members about point B. Clockwise, negative, counterclockwise, positive. What about this load F? Well, this load F, we realized that we'd better to have its component in X and Y. So in that sense, let's call this angle alpha, like here. I can find out alpha, right? Alpha, if I write it down over here, tangent alpha is equal to how much? 200 divided by 300. So from here, I can find alpha. I'll let you guys to find it. So if that's alpha, then this guy also is alpha. And simply, the component of these loads are going to be 2 components, F cosine alpha and F sine alpha, right? And we have alpha. So now it's easier to take moment about point B by these 2 loads. Let's continue. This F cosine alpha, try to rotate it clockwise, so it is the it's a negative number multiplied by 200, the distance, and this F sine alpha, the same. Try to rotate it clockwise, multiply by the distance, which is 160 plus 140 gives me 300, equal to 0. From here, we can find F, which I let you guys to do the math and find out F. So here, if we made a mistake, if in the first place we did a mistake, and let's say by mistake we select F, a tension load, we got the same result, but with the negative numbers. You can try it later. So other two tools that we have, sum of the forces in x equal to 0. What do I have in x? I have f cosine alpha. Remember, always to the right is positive. I have minus 600. And I have bx equal to 0. From here, easily I can find bx. And other tool that I have, sum of the force in y equal to 0. In y, I have f sine alpha. I have by. And I have minus 400 equal to 0. Easily, I can find by, right? So, as you can see, it's very easy. When we get to these free body diagrams, then the rest is just simply following these three basically formula that we have. Please continue the solution and try to find out the numbers for f, bx, and by. And remember, when you have a joint like B, which has bx and by, you have to find the total B, which is bx squared plus by squared. So you need to find out this force B, because when you design this joint, remember, or bolt, you need to calculate the stresses here in this B, joint B. So you need to know the force here. All right? Any question? All right. Go ahead.
I have a quick question about, so the external load at the 400 Newton, wouldn't that be clockwise rotation, not counterclockwise? I'm just having a time visualizing.
Yeah. Try to imagine this link being connected at point B, right? Try to visualize this link B. Forget this 600. This link B, and like here in this image below, right? If you put a weight on top of this one, it's gonna fall to the left or to the right.
I'm sorry, I can't see your point.
Okay. So here on this image, can you see now? The cursor, can you see it or no?
No, I can't see it. I don't know if it's just me.
All right. So let's try this one. So in the image below, right? In the image below, if we say that things can rotate around point B, right?
Yeah.
If you put a weight of 400 here, a weight over there, this weight is gonna fall these things to the left or to the right?
It would be to the left. Yeah.
To the left, right? If it is to the left, then how it's rotating?
Then it's rotating counterclockwise. Yeah.
Counterclockwise, right? Yeah, it's positive. So always try to visualize it, and maybe try to exaggerate. Then probably it's easier to follow. Okay. Let's look at example 3. I just draw the free body diagrams for you, and I let you guys to continue the solution. But first, you have like 30 seconds to figure out the free body diagrams and try how this mechanism connects or works, right? And I'll try, while you're thinking, I'll try to draw these things for you here. So we have this T-shape, sort of T-shape or whatever shape here. And here, when it didn't say anything, it means over here it has been welded together, right? You don't need to separate them. You just separate, remember, the joints. You take your wrench and open up the bolts and pins and rivets, and then you put the reaction there. Okay. So this is like B, this is C, and this is D. And I can say, hopefully you guys realize that AB is a two-force member. And if it is a two-force member, then you know the rest, right? Okay. So this is the external load. We just put it there. That's, we know it's how much? 9,100 pounds. And we have the information that we need to get its component. That's easy. Let's say this is our X and Y direction. So you guys realize that what is the free body diagram? Ahmad, can you tell me what is the rest? What do I need to put to complete this free body diagram?
So at C, it's a joint or pin. So
exactly. So at C,
yeah.
then it's gonna be what? CX and CY,
Yeah,
right?
yeah.
Okay. What else?
And then the two the AB link.
Okay. What is about it?
So we'll draw a two force member.
Okay,
like,
exactly. Yeah, exactly. So it's a two force member. If it's a two force member, always apply load in the line of action between A and B. It doesn't matter if you put tension or compression, but from this image, we can think that it's more like a tension load, right?
Yeah.
So let's call this one T, or you can simply call it AB. All right. So how many unknown we have? 1, 2, 3. Good. So it means we can solve it, right? I let you guys to finish the solution later. You just need to start with taking the moment about point C. From here, you should be able to find T. Then you write the force in X to be equal to 0. It gives you Cx. And some of the forces in Y equal to 0, which give you Cy. It seems very easy, right? Do you guys agree? Now probably you guys wondering why people think 260 is difficult. So far it's not, right? Hopefully you agree. If so, let's solve. Not solve because we have like 3 minutes. Let's quickly take a look at this one. Let's read it. We have a plier. Let's move myself there. Okay. So we have a plier here. Hopefully everybody have seen a pliers. So pliers, there is like a big joint in the middle here in the center, like a big joint here, like this B. And then you apply a load at the handle. Well, and then you compress something at DC. So here we want to know how much force we're producing at DC. Remember this, here it's a pin or it's a joint connection. We treat it like a pin or joint connection. Okay, so try to draw the free body diagrams. Remember, you need to disassemble things, right? And the trick here is because these two parts of the pliers, each portion we call it a plier, right? That's why we have pliers. They are basically the same, they are identical. So it's just enough to draw the free body diagram for one portion. Let me, while you guys are thinking, I'm just trying to draw something for you. Hopefully you accept it, something like that. Yep. So I drew the lower portion, okay? So this is the external load. Sorry, I drew this portion, the upper portion. So that's the external load. So let's see. Uman, are you there? Can you tell me how we can continue the rest?
To be honest, I was trying to figure that out on my side just now. So
okay, that's good. Fair enough. Let's say Who else has a suggestion how we can continue the rest of these free body diagrams? Don't worry, try something. What about if I say this DC is a two-force member? Is it fair to say?
I don't think it'd be a two-force member because at B there would be forces exerted, right?
No, I mean DC. This part that is there.
Oh, okay.
Can we say?
I think so.
Yeah.
Yeah.
It's a two-force member, right? And we can feel that when you apply this 5 Newton, this DC is sort of under compression. Does that make sense? We want to find out this compression, right? If I draw this member DC here, and I'm exaggerating this one here, right? This DC, so this is D, this is C. So when we apply load, then definitely this DC is under compression. We want to find out this compression load. Let's call it F, right? So if that one is F, this load has to be F, the reaction. What about B? B is a pin. What is about pin? Pin always, we say, has 2 reactions, right? It is Bx and By. That's all. Bx and By. So the rest of solution is really, really simple, right? Let's put this one X. We have this line of action, and we have this guy, right? And we have all the distance that we need. So if I take the moment about point B equal to 0, what do I get? I have 5 multiplied by the distance, which is 70. Remember, we're just looking at this diagram, like this portion of pliers here. Okay, just this portion. So when I apply a 5 Newton load there, right, it creates a moment about point B, which you can guess. Is it, Mohammed, is it clockwise or counterclockwise? This 5. Go ahead.
The 5 is counterclockwise.
Okay, great. It's positive.
Positive.
And then what about F? This F that we don't know.
Would be clockwise.
Clockwise, yeah. This F try to rotate everything's about point B, sort of clockwise. Minus F multiplied by the distance, which is 40, equal to 0. Simply from here, you can find F, which question asks us to find it, right? Very, very simple. If the question asks you to find the reaction at the pin, you just need to write sum of the force in x equal to 0, which gives you Bx equal to 0. Sum of the forces in y equal to 0, which you have minus 5 By minus F equal to 0. You found F here. From here, you can find By. This question didn't ask us, but if sometimes we need to find the reaction at the pin as well. Any question before we leave for this one? So as you see, it's very simple. No matter how complicated a machine or a frame is, you just need to disassemble them, start with free body diagrams, and see how this formula can help you. Okay, if you guys are okay, I just need 2 more minutes to show you this example, but I want you to think about it yourself, all right? So 2 minutes and then we're done. You deal with this problem like this one. It's a machine, of course, because it moves, it does something. How you approach these sort of problems. It looks complicated, but it's not really. It's always free body diagrams. If you could draw the free body diagrams, the rest is easy, it follows. Well, let's see what we have here. So by the way, you guys can see my cursor or no when I move? Yes or no?
Yep.
Yeah, okay, good. So let's see what we have. The first step, remember, when you're solving a machine problem is to understand how it works, which for you guys, you are smart, you know how to figure it out, right? So let's see, we have a handle here, this handle and these things with this triangle at the end. It's connect at point F, right? If somebody apply load P, try to rotate this handle up about point F. Try to rotate it counterclockwise. So far it makes sense. So if you do so, then it seems that this guy here, this link, which is a two-force member, try to then push everything, push this point D to the left. Does that make sense? If you apply load P, because of this DE, a two-force member, you try to push this point D to the left, okay? Now, if you try to push this point D to the left, what will happen to this basically distance here? Like this, let me draw this line here, right? This, if you try to push this point D to the left, right, then you try to close up this CD and DB, right? And if you want to do so, then it seems that CD and BD, they like to be in one line. So what then they need to do is to compress everything's down, right? Compress everything's down. And our job is to find out this reaction force, this compression load here. Okay, so hopefully you guys could follow the mechanism, how it works. If so, then the rest, you just need to start free body diagrams, which I want you to do that. Remember, this is a two-force member. This one is a two-force member. This one also is a two-force member. Two-force members. So that's one thing you need to know. And then this basically cylinder, when you draw the free body diagram for this cylinder, let me draw it over here, right? So first of all, there's going to be a force coming from this link BD. And so let's call this one BD. So it's common to call the name of forces when we have links, like with their name of two ends, like we call this force BD. Or some people say FBD, that's up to you. If you want to be fancier, FBD, that's fine. And then, so this load creates a compression here. And don't forget, there are walls around this cylinder and the walls have a reaction, right? Because there is no friction, at least the question didn't say us anything about the friction. There is N here, and our job here is to find this A. Okay, so that's one free body diagram that I did for you guys. Do it for the rest and try to find out this A. If you couldn't solve it, then send me an email. I'll post a solution for you later. Any question before we leave? Are we good? All right, let's come back, guys, at 10:30. Bye for now.